Alright, so here's a general polynomial that you'll need to factor completely, and it turns out that this is one of these examples that's going to require more than just one technique to completely factor things down. So when you're looking at a polynomial that potentially will require multiple techniques to arrive at an ultimate factored form, your best bet is to start off to take out a greatest common factor from all the terms, if indeed there is one. Taking out a GCF, if one exists, usually makes subsequent factorizations a little cleaner and a little easier to see. So when you look at this, you can see there's nothing that's going to come out in terms of the coefficients. There's no meaningful common factor that would come out of 2, minus 1, 128, and minus 64. So we're not going to get anything out numeric here, but when you look at the variable parts here, all of these terms have at least some factor of x in them. And in fact, the biggest common power of x that appears in all of these terms is 5, the power of x that's on this last one here. So since that x to the fifth is common to all of those terms, we can pull it out as the greatest common factor and then just write out the remains that are left over when you just reduce all these x powers by 5. So that leaves behind then doing that at 2x to the fourth minus an x cubed plus a 128x, and then minus a 64. So there's one stage of this factorization complete. You've taken out a greatest common factor, and now this greatest common factor of x to the fifth, just being a monomial, is done. There's nothing you can do to factor down a monomial any further. But just because you finish one part of a factorization problem doesn't necessarily mean that all the rest of it is fully factored. So whenever you finish a stage in your factorization, look back, look at everything you've generated and see if any of the factors that you have left over, like this one here, would yield to any of the other factorization techniques you've got. And when you think of them, in addition to greatest common factors that we've already run through, we've got differences of squares and sums and differences of cubes for binomials. Well, those wouldn't apply here. We've got various methods of factoring trinomials, but this thing's not a trinomial, so none of those would apply here. But we also do have grouping, and grouping is a polynomial technique, you might recall, that can work on factoring polynomials with an even number of terms greater than or equal to 4. And this thing has exactly 1, 2, 3, 4 terms. So grouping might work on this. So attempt the standard stab at the grouping approach by just taking your polynomial and splitting it into a couple halves, a first half versus a last half, and see now if you can perform little greatest common factorizations on each of those two groups. So if you look at doing that here, this first little group, you can get an x cubed out, and that leaves behind a 2x minus a 1. And now this will be a successful grouping if you can take something out of the second little group, so that when you're done with that little greatest common factorization here, you have exactly the same leftover binomial piece. So here, from 128x minus 64, you can pull out a 64. And you can see that that leaves behind exactly 2x minus 1. So there's the signal for a successful grouping. The 4-term polynomial in the big set of parentheses here by grouping is boiled down to 2 terms, and 2x minus 1 appears in both of them, so you can finish off the grouping now by factoring out that common 2x minus 1. And when you do that, that leaves behind, you can see, an x cubed plus a 64. So you look at this, and the grouping stage is done, and you may or may not be finished, depending on what you've generated. So again, the x to the fifth, that was a monomial you took out at the beginning. There's nothing else you're going to be able to do to factor that down. 2x minus 1 is just a linear factor, so none of our factorization techniques apply to linear factors. But now when you look at this leftover piece here, x cubed plus 64, this is in fact one more factorable form and represents one more step in this factorization, because here you've got a sum, obviously with the plus, of cubes, because the things you perfectly cube to get x cubed and 64 are respectively x and 4. So use that information to write out your last stage here. So we've got this sum of cubes, and we know sums of cubes factor down as a binomial times a trinomial, where the sign in the binomial is exactly the sign in the form of cubes that you started with. You had a sum of cubes up here, so that sum carries through as a plus down there. And then that's bookended by the two things that you perfectly cubed to get x cubed and 64. The thing you perfectly cubed to get x cubed is x. The thing you perfectly cubed to get 64 is 4. So there's the binomial part of the factorization, and you wrap things up now by applying that standard pattern that we've seen in several examples to build up the trinomial factor. So remember, that pattern is square of the first thing from the binomial, opposite sign from the binomial, product of the two things from the binomial, plus the square from the second thing in the binomial. So when you apply that here, the first thing in the binomial is x, so the square of the first thing in the binomial is x squared. Then you do opposite sign from the binomial, so that's a minus. The product of the two things in the binomial, that's x times 4, or 4x. And then you always wrap up by adding on the square of the last thing in the binomial. Last thing here is 4. That squared gets you 16. So there's the trinomial factor that comes out of that sum of cubes factorization. So now, when you scan what you've done here, because you have with that binomial times trinomial completed that sum of cubes factorization, just look to see if there's anything else you can do. Again, the monomial's been done from the beginning. That's a linear factor, can't be factored any further. This is a linear factor now. It can't be factored any further. This is a trinomial, but recall from your prior work with sums and differences of cubes that the trinomial that comes out of a sum or difference of cubes factorization is never itself any further factorable over the real numbers. And that's definitely true here. You could see with our integer-based techniques, there are no factors of 16 that would combine to that middle coefficient of -4. So there it is. We've done absolutely as much as we possibly could with this. We've applied basically 3 factorization types, greatest common factors, followed by grouping, followed by a sum of cubes, to get this fully factored final result.